In this video, I will help you understand the dihedral group with the help of symmetric operations. See, if I rotate this triangle by 60 degrees, it cannot be placed on the original one, not even at 90 degrees and at 30 degrees. But if I give it a rotation of 120 degrees, it can be placed on the original one. Also at 240 degrees, it fits well on the original triangle. This shows that a rotation of 120 degrees or 240 degrees is a symmetric operation for this equilateral triangle. Now, before moving forward, let's understand the basic meaning of a group. A group is a set which has a binary operation defined on it. Now, let's understand the meaning of both the terms. A set is a collection of elements. For example, the set of natural numbers n is the collection of numbers 1, 2, 3, and so on. A binary operation, on the other hand, is a rule which relates two elements of the set to another element. For example, addition is a binary operation. Because we get 1 plus 3 equals to 4, 1 and 3, two elements, are related to another element 4. However, this does not mean that the set of natural numbers along with addition is a group, because a group needs to satisfy certain mathematical properties. Let's take a look at them. Now, this mathematical form of these properties might not be quite intuitive for everyone. So let's take the help of an example. Here, Z is the set of integers, which is the collection of all the positive and negative numbers without the decimal part. Alright? Now here are the properties. The first property is called the closure property. It says that when you apply the binary operation, which in this case is addition, the third element should again be in the original set. As we can see here, 1 plus 2 is equals to 3 is again an integer. In general, adding any two integers will again give us an integer. The associative property says that when you are adding three elements, in general, when you are applying binary operation to three elements, then the order depicted by the brackets does not matter. Which means, see, if you add 1 plus 2 first and then add 3 to it, you will get 3 plus 3 equals to 6. And instead, if you try that you add 2 plus 3 first and then you add 1 to it, you will get 1 plus 5, which is again 6. So in this sense, the order of adding does not matter. So this is called the associative property. Then comes the existence of identity. Identity element is a unique element which, on being operated with any other element, gives the same element. For example, here 0 is the identity element. You can add 0 to any other integer and you will get the original integer back again. Then every element in the group should have an inverse element. Inverse of a particular element is another element of the group which, on being operated with the element, gives us the identity. For example, here in the integers, minus 2 is the inverse of 2 because 2 plus minus 2 gives us 0, which is the identity of the integers. When these four properties are present, we say that the set forms a group along with the given binary operation. But we have one more fifth property, which is called the commutative property. It says that the order of elements while applying the binary operation does not matter. For example, here, whether you add 1 plus 2 or 2 plus 1, you are going to get the same answer, which is 3. When a group has the fifth property along with the first four properties, it is called an abelian group. We will see later in this video that in general, for n greater than 2, the dihedral group is not an abelian group. Now let's create the simplest dihedral group D1. Now let's talk about the possible symmetric operations on this straight line. One possibility is to give it a rotation of 180 degrees. Another possibility is to reflect it. So we have two symmetric operations, rotation and reflection. If you notice, I have colored the line in this particular way to keep track of the original line. We shall denote it by E, which means the identity element. Here, identity operation means applying no binary operation. Means we are not doing anything with the line, so the line remains in its original position. We shall denote rotation by R and reflection by S. Now we can see here that rotation and reflection elements are not different, they are not unique. So let's combine it in one element. Now if I take this R and rotate it once more, I get a double rotation R square, which you can see is exactly equal to our identity element E. The same goes for reflection S, because we know that if we reflect anything 2 times, we will get the original image. So we have these 2 elements, and these are the only 2 unique elements possible. No other symmetric orientation of this line is possible. And these 2 are exactly the 2 elements of a dihedral group D1. Moreover, D1 is isomorphic to Z2, which is the set of integers modulo 2, which is equals to 0, 1. Isomorphism just means that these 2 groups are exactly same. They have exactly same structure. Some letters of English alphabet can also be used to depict dihedral group D1. For example, A gives a symmetric vertical reflection. C does not give symmetric vertical reflection, but it does give horizontal reflection. Similarly, E also gives a horizontal reflection, and Z gives a rotation. So D1 is also the group of symmetric operations of these letters. Now let us create the group D2. For D2, we take this arc polygon, which is formed by 2 arcs. Again, we label the initial orientation as E. Now one possible symmetric operation is a rotation. Then we have a reflection, which is denoted by S. And then we have a rotation followed by a reflection S. So it becomes R into S. Now these are the only 4 symmetric operations possible. See, if I rotate it again, then R square gives the identity element. Similarly, a double reflection S square also gives the identity element. Similarly, the third element, which is R into S, it also on being squared gives the identity element. Now this is a special property which makes this group an abelian group. Now these are the only 4 unique symmetric operations possible, which forms our group D2. D2 is isomorphic to the Kleene 4 group K4. We won't go into its details because this video is about dihedral group, not K4. Now let's move on to D3. For D3, we take the equilateral triangle. We label the first element as the identity element and find all the symmetric operations. One possible is rotation. Then, rotating it twice becomes a double rotation R square. Moreover, we see that if we rotate it thrice, then R3 gives the identity element E. In general, for any dihedral group Dn, Rn always gives the identity element E. Now we can rewrite this equation in the following way. R square into R is equals to E. Now R square is such an element which on being operated with R gives the identity element E. So this means R square is equals to R inverse. It is the inverse of R. In general, we have R to the power n minus 1 is equals to R inverse for any dihedral group Dn. Now let's find the other symmetric operations which are possible. We have a reflection here which is denoted by S. Then we can have a rotation followed by a reflection which becomes R into S. Similarly, we can have a double rotation R square followed by a reflection which becomes R square into S. You can see that all these 6 elements are unique. The orientation of dots is not the same in any 2 of these 6 elements. Now these are the 6 elements of the dihedral group D3. Now let us see how it is not an abelian group. If I take this element S here and rotate it once, it gives me S into R. Now you can see here that S into R is not equal to R into S because the orientation of dots is not the same. So this group is not abelian. In fact, S into R is equal to R square into S. Equating these two, multiplying by S, we get a very important equation. S into R into S is equals to R square, or in general, S into R into S is equals to R inverse. This equation can be used to define the dihedral group in mathematical form. So you see how beautifully we have found all the 6 elements of the group D3. Note that D2 had 4 elements and D3 has 6 elements. In general, the dihedral group Dn has 2n elements. Here are the 8 elements of the group D4. The identity element, single rotation, a double rotation R square, then we have a 3 times rotation R to the power 3, then again we have a reflection, then a rotation followed by a reflection. RS. Then we have a double rotation R square followed by reflection, so it becomes R square S. And then the final element becomes R to the power 3 into S. You can see that we have used a four-sided regular polygon square to denote the elements of D4. Whereas we used a three-sided regular polygon equilateral triangle for D3, which shows that for n greater than equal to 3, Dn represents the group of symmetries of n-sided regular polygon. Here is D4. The generalized dihedral group Dn can be written as follows. Either we can write all the elements or we can denote in the mathematical form. Before I end this video, here are the 12 elements of the group D6. And finally, here are the 16 elements of the group D8. I hope this video helps you understand and appreciate the beauty of this dihedral group. This was all in today's video. Thanks for watching.